Test, test.
Test, test.
Good morning, everybody. Welcome to Dr. Hugh Ross's Paradox class. Good to see live faces here, and welcome to everybody online, and welcome to everybody who's listening to this later in the week or the month or next year. We're glad you are with us. Today, Dr. Ross is going to be with us, and he's going to tell us all about his mountaineering adventure last week with his sons, and he's going to talk today about the James Webb Telescope and what it's teaching us about God's universe. Next week, I'm going to finish my little two-part series on near-death experiences, and the 3 weeks after that, which is September 1, 8, and 15, Dave Sargent is going to be teaching, and then Hugh will be back with us all the way through November. So tune in, put your seatbelt on, it's going to be a good time. Thank you to everybody who brings treats. It's a good system we have, this non-system. If you partake of treats, please consider bringing something for everybody else, and it works out really well. There's always lots of empty calories over there, and some really good stuff too. Thank you for everybody in the back there that does the technical stuff. We're still looking for one extra person to help in the future because Mark DeCaro and his family are abandoning us. They're moving to Boise, Idaho, and we're going to need somebody else. So if you know anybody who's good with 3, Jamie says we need 3 people just to replace Mark DeCaro. That's how good he is. Okay, let's see. I guess that's it. Let's say a prayer and we will get to Dr. Hugh Ross. Heavenly Father, as always, we're so grateful. Lord, we just thank you for this class. Thank you for what this class has meant to so many people for so many decades of Hugh's teaching. We thank you, Lord, for his faithfulness and his scholarship and his knowledge and his energy in teaching this class, Lord. We just thank you. It's been so meaningful, such a big part of so many of our lives, Lord. Ask your blessing on us and Dr. Ross as he teaches, and each of us as we go our way this afternoon. Thank you, Lord. In Jesus' name, amen. Please welcome Dr. Hugh Ross.
Well, it's good to be back with all of you, participating here in person, also online. And yes, as Ross just mentioned, last week I was in the Canadian Rocky Mountains with my two sons. One of these things where they drop you off in a place where there's no roads, no people, no trails, no internet, and you just hike around and climb for a few days. Then the helicopter comes and picks you up, and you're out. But I'm learning I'm not as young as I used to be, and so I had a hard time going downhill. This is one of those rare things where there was more downhill than uphill, a lot of uphill, but there was one day where we were descending 4,000 feet down, and it was a route I'd been on before, but they changed the route. And so I was used to being up high and gradually coming down. This time was a lot of steep down. I wound up getting a stress fracture in my right leg. It hurt a lot and made it difficult for me. My sons kind of helped me out, but found out that you don't need a cast for it, just need to let it heal. So I'm letting it heal. So, but I posted one photo of, I took a lot of photos, I always do it, I'm in a beautiful place like that. But I posted one photo on my Facebook page and Twitter page this few days ago, and this is the photo I posted. It's Mount Arras, named after a famous battlefield that the Canadian Army fought on in France in World War I. And I liked it because it's the best example I've seen of what's called an anticline. An anticline is where you got sedimentary rock layers that are flat, and then plate tectonics tilts it up and actually bends it. And what's interesting, you can see the obvious bend to the left, but if you actually look below that bend, you see much more extreme bending. So you see this, then underneath that, you actually see something that looks like this. It's very complicated, and it's different parts, but you get a complete parabola below that. And to me, it was just beautiful. And also, you're looking at 7,000 feet of vertical relief there. I mean, this is a big mountain, and it just rises up from this river, literally 7,000 feet within just a few thousand feet of horizontal. One of the more spectacular examples of what's called tilted and bent anticline. And I posted it because I thought it was really beautiful, but it generated a storm. As of this morning, 375 comments and questions that were posted, and kind of took me off guard, but realized it's relevant to what I spoke about the Sunday I was here before I went on this trip with my sons. Remember, we kind of did a review of what the Bible says about Noah's flood. Well, it turns out about 300 really weren't comments. They were mainly complaints and insults that was being thrown at me, because they said, Dr. Ross, you're implying that this was something that was generated by powerful enduring plate tectonics. This was caused by the flood. And so they threw what's called the hydroplate theory. And I've dealt with that in the past. In fact, I debated the author of that theory some 30 years ago, Walter Brown in Arizona. And his theory, and I thought this theory had completely gone away. No, evidently it's very much alive. It's the idea that before Noah's flood, there was a crust of the earth, but below that crust was an ocean of water. And then what causes the Noah's flood is that the crust buckled and broke, and it released all this water. And basically, citing what you see in Genesis chapter 7, how God loosed the fountains of the deep and all this water came up. But they're talking about an enormous amount of water trapped below the crust of the earth. It's thrust up into the atmosphere, and that explains the 40 days and 40 nights of torrential rain. And, I kind of looked at that and said, if you got that much water being pushed up into the atmosphere, enough water to cover all the continents and mountains of the earth, then water is a greenhouse gas. You throw that much water up into the atmosphere, it's going to heat up the surface of the earth, and it's not only going to cook everybody on board the ark, it's going to evaporate all the water on the whole face of the earth. So I thought, surely this has gone away. But no, it hasn't. And, the hundreds of comments I've been getting is, Dr. Ross, how can you call yourself a scientist? The only way these sedimentary rocks can be bent like that and tilted up is if they're wet. And they got a point. If you got wet, soft, sedimentary rocks, that can be bent, and it can be bent fairly quickly. And my response is, well, you can also bend these rocks if you bend them slowly through plate tectonics. I think a lot of you have been used to that. You can actually take an iron bar or an iron thing, and if you very strongly stress it over a long period of time, you can bend it. You see that in your own homes, is that, very rigid structures can be bent over a long period of time if they're continually stressed by a significant force. That's really what generated this. And the bending took place over a couple of 100 million years. And as I mentioned, the bending is even more extreme below that arc that you see to the left. But the other problem with a hydroplate theory, if you're going to bend the rock layers that much and thrust them up by 7,000 feet, you need a lot of tectonic activity. And that's the irony of the hydroplate theory. They're rejecting mainstream plate tectonic theory, but injecting their own, where they're saying, yes, there was these soft, wet layers of sedimentary rock. They were bent, then they were thrust up 7,000 feet just in the space of a few months. Well, how do you thrust up something that high in just a few months? And they say, oh, tectonics did it. But now we're talking very aggressive tectonics. And, tectonics we're used to. How many of you have been feeling the earthquakes have been going on here in Southern California? I missed a couple because we were in British Columbia where we weren't feeling earthquakes. But, those earthquakes you were feeling, that's ground movement of a few millimeters. I do remember one especially disturbing earthquake that my wife and I felt where the ground moved about 2 centimeters. And that 2 centimeters of movement, or the space of a few seconds, was enough to destroy the furniture in our bedroom. So now we're talking multiplying that 2 centimeters up by 7,000 feet, or more than 2,000 meters. So you can work out the math. Take 2,000 meters, divide it by 2 centimeters. How much energy has to be released to push it up that high, that fast? Well, the energy is actually enough to vaporize every plant and animal and bacterium on the face of the earth instantly. It's enough to evaporate all the water so there's no water on the face of the earth. There would be no water for Noah's ark to float in. There'd be no ark. The ark would be vaporized as well. And the biblical text is quite clear that didn't happen. But again, I was kind of caught off guard. I thought surely this hydroplate theory has disappeared decades ago. Very much described. That's not the case. Well, I'm going to be posting a few more photos because it's a really gorgeous place I was in. And the one thing I like to do on my Facebook and Twitter page is make the point. We human beings are living on planet Earth at the most scenically beautiful time in the entirety of Earth's history. Here we live on a planet that's 4.5662 billion years old. We're living in a 10,000-year window, a unique window when we get to enjoy scenic beauty like our planet has never had before. Do you think it's an accident that God put us here at the most beautiful time in the history of the earth? It's also the same window of time in which we have 10,000 or probably 10 million species of life. Planet Earth has never had such a great diversity of life as it has during the human era. Now, we've gotten rid of a few, but when God created Adam and Eve, literally the diversity of plants and animals was at the maximum point it's ever been. So God has put us here at a time to enjoy the beauty of his creation to the maximum. Well, what was advertised on my Facebook and Twitter page and on Paradoxes, so I'm going to address today, is kind of a lay-level version of what happened at our workshop on July 13th, just a month ago. We held a workshop where we invited astronomers and physicists from around the world to join us in a dialogue. What is the James Webb Space Telescope telling us about the universe? What is it telling us about creation? Does it still comport with the creation model, the cosmic creation model that the Bible has taught for thousands of years? So that's what I'm going to do, but before I do that, I want to show you the latest released image from the James Webb Space Telescope. And to give you some context, the James Webb Space Telescope has 7 times the collecting area of the Hubble Space Telescope, and was basically launched to give us insight into what's referred to as the cosmic dawn. That's that epoch, early epoch of the universe when stars and galaxies were first forming. But the most powerful telescope that astronomers have at their hands is a natural telescope, gravitational lenses. And just to give you a quick review, when Einstein came up with his theory of general relativity, he said, if my theory is correct, massive bodies will actually bend a beam of light around the mass. And the solar eclipse of 1919, they actually saw that the positions of stars next to the sun during a total eclipse changed. They were bent by the gravity of the sun, which means that if you've got a just right massive body between you and a more distant body, it will act like a magnifying glass. It will actually bend the beams of light around the massive body and magnify what you're seeing in the distance. Well, this is one of the best images of a gravitational lens. And what you're seeing here is a nearby galaxy, a big galaxy, bending light from a distant quasar almost exactly behind it. If the gravitational lens is most efficient when you're looking, say, at a quasar, and the light of the quasar is being bent by a galaxy that's exactly in the line of sight. And you can tell here it's very close to being in the line of sight because you see a ring of light all around the galaxy, the nearby galaxy that's bending and focusing the light. And so what we're seeing is the image of the galaxy in which the quasar exists. That's kind of the circle around it. The quasar is a supermassive black hole at the center of the galaxy. So it's a very bright point of light, and you can actually see that the quasar is being imaged 4 times. 3 bright dots at the top and 1 not quite so bright dot on the bottom. And they say, well, why don't we see dots all the way around? Well, it's not a perfect gravitational lens. No gravitational lens is exactly on the line of sight. And so the fact that it's slightly off, but this is so close to being the line of sight, we get 4 really good images of that quasar. It's 6 billion light years away. And what these gravitational lenses do, they magnify the images of very distant objects by as much as 8,000 times. So when you combine the James Webb Space Telescope with a gravitational lens, you get an extremely powerful telescope. Matter of fact, astronomers have even been able to do this with stars, where they will use a star in our galaxy as a gravitational lens to lens the image of a planet in another galaxy. We've actually detected planets in other galaxies by using a star that's exactly on the line of sight that bends the light so we can actually see this faint planet even though it's in another galaxy. So we got the Hubble Space Telescope, we got the James Webb Space Telescope, and we got hundreds of these gravitational lenses. So the combination is incredibly powerful in imaging distant objects in the universe. But what I really want to talk about, there's been a big debate on the internet, claims that the James Webb Space Telescope has destroyed the Big Bang creation model, and that Christians have been wrong all along about the Big Bang. That's the story you keep hearing over and over again on the internet. And to me, I'd like to quote Yogi Berra. Yogi Berra said, "It's deja vu all over again." You know, he was more famous for his little quips than he was for his baseball, as famous as he was for his baseball. And yes, this is deja vu. When I started hearing all these comments, James Webb is finding all these early galaxies that are too bright and too early in the universe. This doesn't fit the Big Bang model. It says, yeah, this is deja vu. And at the workshop we had, I was the oldest of the astronomers that were speaking. And I said, I'm old enough to remember when this happened back in the 1960s. Now, I was a teenager at the time. And that's when they discovered the first quasars. And so this is the first of the quasars that was discovered, 3C273. It's a radio source discovered by the third Cambridge catalog, and discovered in 1963, the very first quasar. And it mystified astronomers because it measured to be distant and very bright and with no discernible diameter. So extremely, just kind of, they call it a quasi-stellar object because it looked like a single star, and yet it was shining with the brightness of literally hundreds of galaxies. And the assumption was, this is impossible in a Big Bang model. And that's when you had people like Fred Hoyle and Chip Arp, Alton Arp, and people like Jeffrey Burbidge saying, we got to toss out the Big Bang. The Big Bang cannot explain quasars. And so they're basically saying these quasars are too bright. They vary too much in brightness, and if they vary that much in brightness, the energies we're talking about are too extreme to be able to explain in Big Bang cosmology. They're too distant, and there's only a few of them. And in fact, people like Chip Arp are saying they can't be that distant. They've got to be much closer. Maybe they're things that are being ejected by nearby galaxies, and therefore we're not dealing with the extreme energy conditions. And this is a way to explain it. So yes, all over the internet, there was no internet back then, but all over the popular media, they were saying quasars prove that the Big Bang is wrong. Well, I was a graduate student at that time actually doing research on quasars. And I said, well, what of these things are the cores of galaxies where there's a very strange energy mechanism that explains why these things are so tiny and yet so incredibly powerful and bright? And I had a difficult time getting my PhD because I was making claims that a number of my astronomers who were on my examining committee said, hey, this doesn't work. They believed in the Big Bang and said this doesn't fit the Big Bang. I said, well, I believe in the Big Bang too. Big Bang is what brought me to faith in Jesus Christ. I wasn't against the Big Bang, but I was saying, I really do think that they're really that powerful and that distant. Well, they said, well, if that's the case, where's the galaxies? We don't see the galaxies. And so I remember in my thesis, I kind of looked at the images that were taken from the Mount Palomar Sky Survey. I thought maybe I can barely see the galaxy, but I couldn't convince the astronomers on my committee. They said, well, it looks pretty fuzzy and faint. We're not sure you've done it. Well, today we now know that indeed quasars are at the cores of giant galaxies. How they discovered that is they block out the light of the quasar so that the light of the quasar doesn't completely obliterate the image of the galaxy, and you get to see the galaxy. Not easily. This is 3C273, where they used a special light blocking device on the telescope to block out the light of the quasar, and yes, now you can see the background galaxy. It's really the only way you can see the background galaxy. That technology did not exist when I was working on my PhD. The other thing that's different is we now know we're not talking about 1 or 2 dozen quasars. We're talking 1 to 3 million quasars. At least 1 million of them that's been discovered. Astronomers think that 3 million of them exist. We also understand what explains the energy output of these quasars and why they're so tiny. They're black holes. Now, when I was a graduate student, we were just discovering evidence for black holes, but the assumption was black holes are no bigger or no more massive than stars. We now know what powers a quasar are black holes that weigh hundreds of millions of times the mass of our star, the sun, even billions of times. And when you get a black hole that massive, the gravity is such it can pull in huge amounts of gas and dust. It can even gobble up stars and gas clouds and even lots of stars, globular clusters. And when it does that, as it approaches the event horizon, that matter is being converted into energy with 8 to 42% efficiency. So now we understand how quasars can be so extremely bright in the context of a Big Bang creation model. But that took 35 years before astronomers realized quasars are not a threat to Big Bang cosmology. They're actually predicted by Big Bang cosmology. But it took really understanding the physics of black holes to get us there. What I'm basically suggesting is, yes, we're seeing observations from the James Webb Space Telescope that seem to be really difficult to explain in the context of the biblically predicted Big Bang creation model. But if we're patient, we're going to understand the physics that we don't understand right now. And isn't that the reason why we launched the James Webb Space Telescope? To give us a deeper understanding of the universe. So what I was saying at the workshop was, it's too soon to panic. The James Webb has only been up for 2 years. It's got a 30-year mission. And we're anticipating it's going to take that long to really give us all the reasons for why we set it up. But these are basically the challenges we're getting from the James Webb Space Telescope to what's called the standard Big Bang creation model. Number one, we're seeing cosmic dawn galaxies that are way too bright. Say, what's a cosmic dawn galaxy? That's a galaxy that forms between 200 million and 1 billion years after the cosmic creation event. The context there is the universe remains free of stars until about 200 million years ago. So you can't get galaxies until you get stars. You can't get stars until the universe is about 200 million years old. And so these are the very earliest galaxies that form the universe. And yes, the initial observations from the James Webb Space Telescope said they seem to be too bright and we seem to be seeing too many. So we got a problem here. But that's exactly what happened with quasars, is that when we looked at these quasars, they were too bright. Well, here's the issue. The brightest ones are the easiest ones to discover. So of course, the first ones you're going to find will be the brightest ones. And so just like the first quasars we found were the brightest ones, and it took telescope technology to see the millions of quasars that are not so bright, likewise, I think we need to be patient. Of course, the James Webb Space Telescope is going to detect the bright, early galaxies first, and the millions and billions of faint cosmic dawn galaxies will not be discovered until we do much longer deep sky observations with the James Webb Space Telescope. That is scheduled, but it hasn't happened yet. Hubble, they did one exposure of a small part of the sky that was devoid of stars, and they let the telescope integrate for 2 whole weeks. And they were able to see what's called the Hubble Ultra Deep Field, and they were able to detect these faint galaxies and concluded there must be 200 billion galaxies in the universe. They've yet to do that with the James Webb Space Telescope. So we're not finding the faint ones yet, because that's been the big challenge. There's way too many bright ones compared to faint ones. Well, you can't really say that until you've done a deep enough survey to find the faint galaxies. Of course, the ones you're seeing right now are the brightest galaxies. So it's saying the cosmic dawn galaxies are too bright, they're too numerous, and it looks like these supermassive black holes appear too soon and are too massive. In other words, we're seeing quasars in the cosmic dawn. The anticipation was we wouldn't see them until the universe is about 1 billion years old. But we're actually finding quite a few quasars when the universe is only 400 to 700 billion years old. How do you get supermassive black holes forming that early? That's a challenge. And the other big challenges are saying, well, James Webb was supposed to find these metal-free stars that the Big Bang predicts. Okay, a little bit of background here. In Big Bang cosmology, you have a space-time creation event. An agent outside of space and time creates this little ball of space-time. So you basically got the universe of 10 space-time dimensions being created by this agent outside of space and time. And the factor there is, if you look at Hinduism, Buddhism, they teach that gods create within space and time that eternally exists. Unique to the Bible is the declaration that no, the creation of the universe is the creation of space, time, matter, and energy. Space and time are not infinite. They are not eternal. They were created when God creates the universe. Well, okay, so the universe begins with 10 space-time dimensions collapsed into a very tiny ball, infinitesimally small. But the Creator created that space-time ball with the property of ongoing expansion. And so that little tiny ball began to be stretched out. As it stretched out, space curvature was released. The universe became less and less curved. And that release of space curvature first generated photons. So at the very beginning of the universe, there's no light. But you get light by the time the universe is a trillionth of a trillionth of a trillionth of a second old. So the light shows up pretty quickly. And if you wait long enough until the universe is about a 10 billionth of a second old, you get matter. That's when you start getting quarks and gluons, which become protons, neutrons, and electrons. So yes, by the time the universe is a 10 billionth of a second old, you got matter, energy, space, and time. Okay, but you only have one element at the beginning of the universe, hydrogen. Hydrogen is a single proton. And so the universe, after a 10 billionth of a second, it's filled with protons, neutrons, and electrons, but none of them had a chance to condense yet to make atoms. There's only hydrogen. But the universe continues to expand. As it expands, it gets cooler and cooler. It's the same principle of your automobile engine. When the piston chamber expands, the gasoline stops burning. And so the piston collapses, it burns again. So the universe expands, the temperature goes down. And there's a window of time about 20 seconds old in Big Bang cosmology where those little protons can be fused into helium. And that happens when the universe cools down enough to be 150 billion degrees centigrade. And it continues until it cools down to about 17 billion. So that window, 17 billion to 150 billion, that's when those protons can be fused together to make helium. It all happens in just 20 seconds. In 20 seconds, you get about a quarter of the hydrogen being fused into helium. But after that, no more fusion can take place. So you get a little tiny bit of lithium, and we're talking very tiny, 100 millionth of a, 1/100th of a millionth of the quantity of the hydrogen gets made into lithium. And you know these lithium batteries you have? All that lithium was made in the first 4 minutes of the universe. Stars don't make lithium, they destroy lithium. So you better conserve the lithium you got because once we're gone, it's gone. The stars aren't going to make any more. So, but yeah, it's hydrogen, helium, and a very, very, very tiny amount of lithium. Everything else is made by stars. So, one of the big predictions of the Big Bang creation model is that we will find stars, or we will find gas, if we look far enough away, far enough back in time, that all you see is hydrogen and helium. And if you got a powerful enough telescope, maybe a trace amount of lithium, but there'll be no carbon, no oxygen, no nitrogen, nothing heavier than lithium will show up in the spectrum. Now, one of the advertised missions of James Webb was to find these what are called pristine stars that are made up only of hydrogen and helium. But I've been telling people for quite some time, over a decade, that James Webb is not powerful enough to find those stars. What's going to happen is those stars will be, they have to be so far away because, yeah, you can say, well, what about the biggest stars? They'll be bright, but those biggest stars burn up in only a few 100,000 years. The only way you can see them is if you look 13.6 billion light years away, and you're looking that far away, no telescope has the power to see a single star. So they say, well, maybe if we got a whole cluster of stars, maybe we can find those pristine stars that are only made up of hydrogen and helium. But that assumes that they all form at the same time. It also assumes that they're all very massive. And we already know star clusters don't form that way. There's always a distribution of masses. So you're bound to see the ashes of the big stars polluting the gas that's collapsing into the smaller stars. But that's been a major complaint, especially thrown up by young Earth creationists. If the Big Bang is right, where are these metal-free stars? Okay, but no metal-free stars have been detected. Now, one of the things that a lot of lay people don't understand is that one of the strongest evidences for the biblically predicted Big Bang creation model is that we've gone from a recognition it looks like the universe has some kind of Big Bang creation event to be able to come up with a more detailed and progressively more detailed Big Bang creation model. So if you go back to the 1920s, the Big Bang model was, well, the universe expands from a small volume, and there's a beginning. And then you had people saying, well, it's not a cold Big Bang, it's a hot Big Bang. That was about the 1930s, mid-1930s. George Gamow was saying, it's not a cold Big Bang, it's a hot Big Bang. So we've gone from a generic Big Bang to saying it's hot. And then with the space-time theorems coming out in the 1970s, they said it's not only hot, it includes a beginning of space and time itself. And so the proof that space and time at the beginning actually gave us a Big Bang model. Okay, it's expanding from a small volume, space and time at the beginning, and the beginning is very hot and it's cooling down. Then we move into the 1980s, and they said it looks like the geometry of the universe presently is flat. Yes, it started off curved, but now it has a flat geometry. Now, it's four-dimensional flat. Don't try to think of it as three or two-dimensional flat. Don't try to visualize it. It can't be done. But what we mean by a flat universe, it's at the very edge of expanding forever and expanding and collapsing. That's a flat universe. And then you go into the 1990s, and they said, it looks like it's not only flat, it looks like there's an event when the universe is about 10 to the minus 35 seconds old, where it expands at millions of times the velocity of light, but only for a very split second, less than 10 to the minus 32 seconds. And kind of the picture is this. The universe starts off about the size of a proton, and it expands millions of times the velocity of light and becomes the size of a grapefruit. See, that doesn't sound very dramatic. Well, it's incredibly dramatic when you realize all that happens in about 10 to the minus 33 seconds. To get it happen that fast, yes, it has to expand millions of times velocity of light. If that didn't happen, the universe would not be thermally connected today, or the universe would be too small. So small the stars would be too close together. A condition for life to exist is that the stars be far enough apart and the universe be thermally connected. That can only happen with that early inflation event. And now it's referred to as the standard Big Bang creation model. It was what's called the Lambda CDM model. Astronomers love acronyms. And what's particularly annoying for lay people, they don't only use Roman letters in their acronyms, they throw in Greek letters, in Hebrew letters. So lambda is the capital L in Greek. And that's the symbol for dark energy. And CDM is an acronym for cold dark matter. And so we've learned enough about the universe to realize it's not just any kind of Big Bang. It's a Big Bang universe where most of the stuff is dark energy, and the second most dominant component of the universe is cold dark matter. And so one of the strongest evidences, scientific evidences for Big Bang cosmology, we've gone from a very general Big Bang model to a progressively more specific and detailed and constrained Big Bang model. And actually, one of the missions of the James Webb Space Telescope was to narrow that even more. Okay, we now know that the viable models are models where the universe has a hot beginning, a space-time beginning, where there's an inflation event, where most of the stuff of the universe is dark energy, and most of it, the second dominant component, is cold dark matter. But let's use the James Webb to come up with an even more constrained Big Bang creation model. And so people think we astronomers have one Big Bang model. We don't. We have dozens of lambda CDM models. So here's the family of lambda CDM models that are being researched. Okay, it's possible that yes, the dominant component of the dark matter is cold, but maybe it's accompanied by tiny amounts of warm dark matter. And so one of the questions is, well, is there any warm dark matter? Is it 5%? Is it 1%? Let's use the James Webb to discover whether or not, let's actually look at what's the third most dominant component. Okay, number one, dark energy. Number two, cold dark matter. What's number three? Let's see if we can figure that out. Let's see if we can determine what kind of inflation event happened at 10 to the minus 35 seconds after the cosmic creation event. So there's dozens of models that posit different kinds of inflation. And what about dark energy? In fact, I just posted a news of the day at reasons.org. It's a 15-minute video clip that you can watch on our YouTube channel. It looks like we're actually determining what kind of dark energy is the responsible for the expansion of the universe. But we like to get even more detailed. And what about dark matter particles? We haven't discovered any yet, other than neutrinos, which make up only a tiny percentage. What about the dominant components? And what about these first stars? And that is one of the primary missions of the James Webb Telescope, to detect the first stars in the universe and determine, are they really massive or not so massive? How many form? Do a lot form or only a few form? And so we have a whole family of Big Bang models with different positions on this. So it's not that the James Webb Space Telescope is challenging the Big Bang creation model, it's challenging some of the subcategories of what's referred to as the lambda CDM model. And that was its goal. And so, no astronomer is thinking, hey, we're in trouble on the Big Bang. No, we're actually making progress in determining, okay, these dozens of lambda CDM Big Bang creation models, which ones are correct and which ones are wrong. And the core of that is determining these first stars that are made up only of hydrogen and helium and a trace amount of lithium, what are they like? We don't know that yet, but that's one of the missions of the James Webb Space Telescope. But a couple of things we do know. In the present era, it's impossible to get a star to form that's bigger than about 150 times the mass of our star, the Sun. The reason why is the universe is now filled not just with hydrogen and helium, but carbon, nitrogen, oxygen, lots of other stuff. And those extra elements basically prevent very big stars from forming. But astronomers have known that if you don't have carbon, oxygen, and nitrogen, and phosphorus, and all those other elements, no iron, that it's actually possible to get stars much bigger than 150 times the mass of our sun to form. And so one of the missions is, okay, are these first stars 1,000 times more massive? Maybe 300 times more massive? 500 times more massive? What's the limit? Now, this actually has a bearing on why we're seeing several dozen really bright, early galaxies. Because the brightness of a star goes up with a 3.9 power of the mass of the star, and just to kind of round it off, the 4th power. So to give you some context, if you've got a star that's 1,000 times more massive than our star, the sun, it will shine 1 trillion times brighter. 1,000 times 1,000 times 1,000 times 1,000. So yeah, so if you get stars even at 400 times the mass of our star, the sun, it's still going to be incredibly bright. And you only need a few of these really big stars to explain why these early galaxies are as bright as they are. Okay, but one of the challenges that we've been seeing is that, okay, we found galaxies 400 to 800 million years after the Big Bang creation event. It looks like the abundance of carbon, oxygen, and nitrogen is too low. I mean, we see in the universe today is if you've got stars forming, the big ones will burn up quickly, and when they burn up quickly, they basically blast in a supernova eruption all the ashes of their nuclear burning. And those ashes are carbon, oxygen, nitrogen, magnesium, iron, and all the other elements. And so they said, well, when you're at 400, 800 million years after the cosmic creation event, even if the first stars are coming in at 200 times the mass of our star, the sun, there should be a lot of ashes in the universe. Why is it that these early galaxies seem to have 4 times less of these polluted ashes than stars, than galaxies that exist when the universe is 2 to 13 billion years old? Well, a paper got published saying, hey, it's really quite easy. The early universe is filled with gas that's only hydrogen and helium. And yes, you've got stars forming, and big stars are throwing out the ashes of their nuclear burning, but those ashes are being diluted by the original pristine gas. That pristine gas today is all gone. There's none of it left. But in the early universe, you've got lots of gas in the universe where stars haven't formed. And therefore, that's going to dilute. And they actually calculated what the dilution factor would be. It's a factor of 4. So it basically explains what we're observing. It should be a factor of 4, and that's what it is. Well, what about these early galaxies? Well, one of the things that really got lay people excited or disturbed is that astronomers found 90 candidate galaxies. When they say candidate, that means we're not sure we've discovered it to be a galaxy in the cosmic dawn, but we're fairly confident that at least a third of them are not going to be just candidates, but actual galaxies existing in the cosmic dawn. But as I looked at these galaxies, on the assumption they really are early existing galaxies, their brightness at ultraviolet wavelengths was 10 times too high. Well, I remember reading the research paper that were making these claims. Their ultraviolet brightnesses are 10 times too high to fit a Big Bang creation model. But as I read the paper, I realized they were assuming that star formation in the first, well, from 200 million to 1 billion years, that the star formation occurred at a constant rate. It's like, now wait a minute. There's hundreds of papers published that make the point that when you go from 2 billion years after the cosmic creation event to the present day, star formation doesn't happen at a constant rate. It's stochastic, which as a technical term means it does this. So you get periods where you get extreme star formation going on, then you get lulls where hardly any goes on. And so a paper finally got published where they said, well, let's assume that star formation in galaxies happens the same way in the first billion years that it does for the rest of the history of the universe. That it's like this instead of like this. When they did that, they got ultraviolet luminosities 10 times brighter. So it basically explained exactly what they were observing. But perhaps the most stunning discovery was this galaxy GN-Z11. You got to love these astronomers. They come up with these very colorful names for the galaxies that they discover. They're all license plates, and some of them actually have as many as 20 numbers and symbols. Why don't they just come up with some nice, attractive name? But they don't do that, probably because there's so many of them. And the Z11 means we're seeing it at a redshift of 11. What does that mean? It means we're seeing this galaxy as it is just 410 million years after the Big Bang creation event, which tells us it's so young that it's only been able to form stars for about 220 million years. And so look at this galaxy. It had a small diameter, but an extremely bright core. So it was small, but very bright. And the core was so bright that it was equivalent to 20 trillion times the brightness of our star, the sun. And this is what led astronomers to discover, it really does look like these firstborn stars, at least many of them, are extremely massive. Because there can't be a lot of stars given the small diameter we saw. We're looking at thousands of stars. But if we got stars that are 300 to 1,000 times the mass of our star, the sun, you don't need very many. You only need hundreds to get 20 trillion times the brightness of the sun. So that was their conclusion, that these stars in the core of this galaxy had to be between 100 and 1,000 times the mass of our star, the sun. And the astronomers that published the paper said at least a good handful of them have to be more than 500 times the mass of our star, the sun. And if you got stars that big, that would imply you get an early forming supermassive black hole. However, a subsequent paper basically said we've used the James Webb Space Telescope not just to look at the core of this galaxy, but to look in its outer halo. And when they did that, they found a giant gas cloud in the halo of this galaxy that had no metals. All it had was hydrogen and helium. So for the first time in history, astronomers have discovered an object of the universe that has nothing but hydrogen and helium. Now, they may do a subsequent observation to see if they can pick up the predicted helium, but the predicted helium is going to be 100 million times less abundant, the lithium, 100 million times less abundant than the helium. But yeah, this is a stunning discovery, something that's predicted by all Big Bang creation models. If you look far enough away, early enough in the universe, you'll find objects that had no elements heavier than lithium. For the first time, they've actually found one. You say, how did they discover it? Well, it's because this galaxy has an extremely bright core, a core of thousands of very big stars. And these stars are packed into a tiny volume, and they're extremely bright, and the brightness is so great that it actually ionized this big gas cloud in the halo. What I mean by ionize, basically threw everything into nuclei and electrons. And when you do that, when you ionize it, you can actually detect what the elements are in that gas cloud. It can only be done if the gas cloud is illuminated by something that's relatively nearby and extremely bright. Well, that was the case with GN-Z11. Extremely bright core. It ionized the gas cloud. They were able to put a spectrum on the gas cloud and discovered all it had was hydrogen and helium, and had it in exactly the ratio that the Big Bang creation models predict. So, a breakthrough discovery, the first time astronomers have discovered pristine gas as predicted by all Big Bang creation models. Okay, let me finish up with this one. Again, you got to love the names that astronomers put on these objects, these galaxies they discovered. JADES-GS-Z14-0. I won't tell you what all the acronyms mean, but JADES is an acronym for a research project. In fact, the joke we had now is at Caltech, we can't begin a research program until we come up with an acronym. The acronym's the first thing we come up with. But only astronomers know what the acronym means. I don't know how that helps. Okay, but the stunning thing about this galaxy is that we're seeing it just 280 million years after the Big Bang creation event, which means you got stars forming for only 90 to 100 million years. And this one has a fairly big diameter, half-light diameter of 1,600 light years across, and it's got an enormous mass of stars, 400 million times the mass of our star, the Sun. That's a lot of stars forming in just 200 million years. So it's basically telling us the Big Bang models that are correct are those models that favor very early star formation and very massive stars being part of those firstborn stars. This ranks as the most distantly measured galaxy. We got candidate galaxies that might be more distant, but this is the most distant one where they got an accurate measure of its distance. They also were able to discover it's not the black hole that explains why it's so bright, it's actually the stars. So it kind of solidified it. The correct Big Bang models are ones where stars form very early, where many of those stars are extremely massive. I just thought you'd like to see an image of another one of these cosmic dawn galaxies. So you can just see they're quite hard to detect. That little tiny red spot, that's it. Okay, well, the latest challenge to Big Bang models is what's referred to as too early supermassive black holes. And yes, I know my time is up. I'll try to wrap this up quickly. Okay, we've now found 4 supermassive black holes in the cosmic dawn. A supermassive black hole is a black hole that's 1 billion times the mass of our sun or bigger. And the thinking was it takes billions of years for black holes to get that big. But now we found 4 in the first billion years after the cosmic creation event. And there's anticipation, hey, if we found 4 already, we're probably going to find dozens, if not hundreds. How do we explain galaxies that are as much as 1.6 billion times the mass of our star, the Sun, forming in just 700 million years? Well, here in closing are 3 ways we can make that happen. You got very dense gas. Keep in mind, when the universe is young, it's much smaller than it is now, which means you got a lot of gas highly compressed. Highly compressed gas being sucked in by a black hole, that black hole is going to grow very rapidly. And what if you got stars that are more than 500 times the mass of our star, the Sun? All of them are going to become black holes. If they merge, you quickly get a really big black hole. But probably one of the most interesting set of papers published was one saying, in the early universe, where all you got is hydrogen and helium, you can actually get gas clouds bigger than 10,000 times the mass of our star, the Sun, that will collapse to make a star. But the star will never shine. It becomes a black hole before it can shine. But it becomes a black hole that's more than 10,000 times the mass of our star, the Sun. That can't happen in today's universe. The carbon, oxygen, nitrogen prevents that from happening. But if all you got is hydrogen and helium, you can actually get gas clouds that big that will collapse and they become a black hole before they ever get to shine as a star. You get a bunch of those forming in a small volume, you quickly get black holes that are 1 billion times the mass of our star, the Sun. Now, I spoke about this at our workshop back on July 13th. Making a prediction, I think, is a combination of all 3 that explains why. And I actually said we're going to find hundreds of supermassive black holes in the first 1 billion years. It's not going to be just 4. We're going to find hundreds because I think the physics of the early universe actually favors all 3 of these mechanisms working. And if all 3 work, we're going to find a whole bunch of those supermassive black holes. Well, let's wait a couple of years and see if I'm right or if I'm wrong. But lastly, I want to point this out. We need to be patient. Let's give the James Webb Space Telescope time to take the really deep images, where they don't just integrate for 20 hours, where they integrate for days on end. James Webb is able to do that. When it does, it's going to reveal the real ratio of faint to bright galaxies. Already, James Webb has taken an image where they found 4 bright galaxies in the cosmic dawn and 50,000 faint ones. That ratio of faint to bright galaxies will tell us what kind of Big Bang universe we live in. Okay, I'm way over my time. You can just look at the rest of this, but my whole point is, like with the Hubble Space Telescope, we needed to wait a couple of decades to get the real answers. The same thing is going to be true at James Webb. Be patient, and I'll try to keep you up to date on the discoveries as they're made. So let's take a question from our online audience, then we'll go to a question here from, that's how we do this. We alternate with people who are online and people that are here in person, and you can bring up any question you want.
Thank you, Dr. Ross. For everyone here in the audience live, if you have a question, come on up and we'll get you in line. We've only got a few minutes left for class time. But online, Hugh, Tinny W. says, hi, Dr. Ross. St. Paul talks about not judging people outside the church, but he passes judgment in the church. But then in James 4:11, he talks about not judging fellow believers at all. How do we as Christians balance discernment with not judging?
Yeah, very good question. And the answer to that is, well, read everything that the Bible says about judgment. And you discover it's a fairly complex subject. And where Paul is exhorting us as believers to judge, he's basically saying it's the responsibility of the elders and the teachers within any Christian community to basically take authority over the moral behavior of people there. And therefore, it's basically telling elders, it is your responsibility to go to people in your congregation that are living in sin and restore them. And so, in that sense, we are supposed to judge. But he also makes the point, don't expect unbelievers to live by the same standard as believers. And therefore, you need to be willing to welcome people into your Christian community that have not yet conquered the sin issues in their life. And none of us have really had a full conquest. We're all on the way. And so we're to judge believers in the church by a higher standard than unbelievers in the church. And we're to judge especially the leaders. The leaders need to be held to a higher level of moral behavior than the rest of the people in the church. So there's different levels of judgment that we're to exercise. And Paul also makes the point, recognize that God has granted authority to the governments of the world to judge the moral behavior of their citizens. And basically says you need to grant them that right. But it also makes the point, no one has that right in their own mind. There is no basis for vigilantism. That kind of judgment can only be done by bodies that have been granted authority by God, whether it be the police, the army, the government, or in the case of a church, the body of elders and teachers. And so there's no room for individuals to do that. So hopefully that helps. We got material at reasons.org that actually goes into all the texts on judgment. I got a book coming out within a few months that's got a whole chapter on the doctrine of judgment. Okay, go ahead.
Yes, just by accident, I stumbled across a piece on the internet regarding this issue of the galaxies appearing to be too mature and trying to resolve, as you've been doing this afternoon. And the one proposal was that our estimate for the age of the universe is what is throwing things off, that the universe is actually much older, maybe as much as 27 billion years as opposed to 14 billion. And that would help resolve some of the difficulties that you've described and yet retain the Big Bang model. Is there any validity to that?
I'm aware of the paper that makes the claim that the universe might be twice as old as what astronomers have been claiming for decades. It's a single paper, and the paper is basically saying if light tires as it goes through space, then maybe the redshifts are not giving us distances in the universe. And keep in mind, if you know the distances to galaxies, that gives you the age of the universe. So they're basically calling into question the redshift method for measuring distances, saying maybe that redshift is at least in part explained by the tired light hypothesis. Now, I wrote about the tired light hypothesis in my book, A Matter of Days, a decade ago, basically laying out that that was something that was hypothesized 40 and 50 years ago. It's been thoroughly refuted by astronomical observations. Personally, I was rather stunned that this paper made it through the peer-reviewed process. Although reading the paper, he says, if light tires, this is what would happen. But we already know light doesn't tire as it travels through space. It doesn't lose energy as it travels through a vacuum. Now, the thing that has been missing in the comments from astronomers against this paper is we already have calibrated the redshift method out as far as 470 million light years. Because the idea was, well, redshifts may not be a measure of the Doppler shift, maybe it's explained by something else. But the Doppler shift effect has been calibrated by direct distance measurements. Now, a lot of lay people think the only way we get direct distances is that we use the orbit of the Earth for the baseline of the isosceles triangle. We measure the angles at both to a distant star, and that gives us the distance of that star without any assumptions. That's what's called a direct distance measurement. And the claim is the baseline of Earth's orbit about the sun is too small to actually allow us to calibrate these redshifts, because these redshifts are distant galaxies. Well, astronomers have come up another way to measure distances directly to very distant objects. Instead of using the orbit of the Earth, they use the orbit of a maser object in a galaxy. And like masers and stars, they all go around the center of the galaxy. And so what they do is they measure one, and a maser is basically a laser source at microwave wavelengths. But astronomers have discovered quite a few of these. They're very bright, they're very small, and if you wait, say, 20 years, you can actually track the orbit of the maser about the center of its galaxy. Well, the diameter of that orbit is no longer just 180 million miles. We're talking a diameter of tens of thousands of light years. So now you've got a really big baseline, and you can use that baseline to measure the distance to that galaxy. So it's kind of the reverse of the standard way of measuring direct distances. But it is a direct distance measurement, and it successfully has measured the distance to galaxies as far away as 470 million light years, basically telling us the Doppler distance is a true measure of its distance. There is no other contributing factor that is significant. So the universe really is 13.8 billion years old. It's not 27 billion years old. And how do we explain these bright galaxies early in the universe? The first stars, at least many of them, are very, very massive.
Thank you very much.
Welcome.
Hugh, Frank McInnes has a simple question. He says, could Noah have landed in Africa?
Could Noah have landed in Africa? Well, we know that humans, in the days before Noah's flood, were constrained to the Near East, the Middle East, or Eastern Africa, not beyond. We see no evidence of human habitation beyond that region until the event you see in Genesis 10 and 11, where God scatters humanity over the face of the earth. Bottom line is the error bar is quite big about what was the full extent of human habitation in the days before the flood. And I also believe that Genesis 8 tells us that the flood waters took a whole year to recede. To take an entire year for the floodwaters to recede, you'd have to have a lot of melting ice. Because if there's no ice, the water flows out quite quickly into the oceans and the flood is over. But if you've got a lot of melting ice, the liquid water flowing out into the ocean can be replaced by the ice that's melting. That's how you get a flood lasting a whole year. But that means, to explain the quantity of ice, the flood is taking place during the last ice age. If it's during the last ice age, there's a land bridge joining Arabia to Eastern Africa. So yeah, it's possible that it could extend as far as Eastern Africa. It's also possible it could be anywhere in the Persian Gulf, because almost the entirety of the Persian Gulf would be above sea level. It could even be part of the Mediterranean, because a good chunk of the Mediterranean also would be above sea level. Bottom line is, it's a pretty big error bar. So I can't give you a very accurate answer.
Yeah, I was having a discussion with a friend a couple of weeks ago. And it's kind of an addendum to what you were talking about, the first part of the class. He claims that it's been shown with the James Webb Telescope that black holes don't exist, which I'll use the Yogi Bear comment to that. But he says there's actually stars inside black holes that have been spotted by the James Webb, and I kind of found that hard to believe.
Find that hard to believe as well, because it is possible for a black hole to suck in a star, but when it does, that star is totally destroyed. Similar to what would happen if you get sucked into a black hole. First thing you notice is your 5-foot long or 6-foot long body gets stretched out to about a 3-mile string of particles. Same thing happens to a star. As it gets sucked into a black hole, it gets strung out of this long line of particles. It goes into the black hole. The particles get destroyed. So there's no way you're going to have a star inside a black hole. The black hole totally consumes the star. And we've got a supermassive black hole, like 1 billion times the mass of our star, the sun. It's probably sucked in hundreds, if not thousands, of stars in its vicinity, plus a whole lot of gas. I've not seen anything like that in the literature. I've not seen anything like that online, but it wouldn't surprise me if there's an online article making that claim, but there's no physical basis for it.
Jared Neal asks, would the distribution of dark matter after SM black hole formation, was dark matter gravitationally collapsing during the first 380,000 years before atoms formed?
Well, we do know that we're still trying to work out the physics of this dark matter. We don't know what particles comprise this dark matter, so that kind of leaves us with some uncertainty. But we already have a lot of evidence that when you get a supermassive black hole, and that's what SM stands for, supermassive, so that's what he's referring to. When a supermassive black hole forms, it attracts dark matter towards it. And so there's a lot of idea, well, how much dark matter gets sucked into the black hole? But we do know that there's a cloud of dark matter around the black hole. And there's stars near the center of our galaxy. Our galaxy is a supermassive black hole that comes in at about 4 million times the mass of our star, the sun. And we actually see some big stars near our galaxy's supermassive black hole that appear to be too old if all they're comprised of is ordinary matter made of protons, neutrons, and electrons. Because if you've got a big star, it burns up quickly. And we're actually finding big stars that are many millions of years old near our galaxy's supermassive black hole. So what astronomers are speculating is that these really big stars that are orbiting close to our supermassive black hole, they're composed not just of ordinary matter, but a lot of dark matter. And if that's the case, it explains why they can continue to shine brightly for 10, 20, 50 million years, even 100 million years. And so there's a new research program going on. Well, we know of a few stars that are in that category. If we can get studies on, say, 100 or 200 such stars, it'll actually tell us exactly how much dark energy makes up those kinds of stars. In fact, one paper was published saying if enough of this exotic dark matter comprises these stars, they can literally shine for 1 trillion years. So that's kind of weird. How you can have a star, say, 20 times the mass of our star, the sun, instead of burning up and going supernova within a few million years, it actually can continue shining for billions and billions of years. Kind of exciting. See where that happens. We need to find more of those stars.
Hugh, I have a question. Are there astronomers that are working in this field who are entertaining the idea that the Big Bang did not happen? Is that a tiny minority, or is there a substantial number of astronomers that believe this? And do they have an alternative, well-developed theory, or are they just beating up the Big Bang?
Well, there are astronomers speculating. You know, we know of 4 forces of physics. Maybe there's something exotic about our universe where we got a 5th force of physics that contributes a very, very, very tiny to the force and energy of the universe. We know it's got to be really, really tiny because we haven't found it yet. But they're saying that might explain some of these odd features what we seem to be seeing in the Big Bang universe. But this is all based on the assumption that dark energy is governed by a single constant. A far more predominant view within the astronomical community is maybe dark energy varies very slightly over the history of the universe. In fact, I posted a news of the day thing a week ago where I said we actually have observations of very distant galaxies and galaxy clusters that seem to be suggesting that is the case. If that's the case, there's no need for a tiny 5th force of physics to contribute things. But you know, it's always, I mean, people know, if I get my name on the discovery of some new constant of physics or some new force of physics, I'll get the Nobel Prize, even if it's just making an extremely tiny contribution. So there's always a motivation within the astronomical community. Maybe I can find something really new. But it's probably more likely that it's going to be something boring, that it's just a kind of a wrinkle on what we already know. And maybe we need to think of a different way of awarding Nobel Prizes in physics. Because, yeah, they tend to be given to something that is totally out of character. But hey, as one critique of the Nobel Prize said, we should be giving the Nobel Prize out to physicists and astronomers who prove things that are wrong, not just things that are right. Because that's often how science progresses, where we actually say, hey, we now know that this is incorrect. But so far, they've never given a Nobel Prize for proving that something is wrong.
What you're saying is then that the number of astronomers who disbelieve the Big Bang entirely is a pretty small.
Yeah, we're talking way less than, say, 1/100%.
Wow.
Yeah, it's tiny, but they tend to get a lot of publicity. And it's not so much the astronomers' fault, it's reporters, news people interviewing astronomers and then kind of exaggerating what they're saying. I mean, that happened to me when I was at Caltech. We had a newspaper reporter come in and talk to a bunch of us astronomers. And the question he asked is, do you think it's possible that there's life elsewhere in the universe? And almost all of us said, well, anything is possible. Well, guess how it got reported? Astronomers at Caltech say life is possible elsewhere in the universe. Wasn't exactly what they said. So, in fact, I remember once being interviewed by the History Channel. And actually, it was somebody they had contracted, it wasn't them themselves. But I'm on the History Channel saying that UFOs explain, beings from outer space explain things like the pyramids. I was actually saying the opposite of what they claimed I was saying. But they took 45 minutes and they took out a 12-second clip and played that. And in fact, one of my colleagues, they actually clipped out the word not. So take with a grain of salt. And you know, that was so disturbing that the 3 of us who were interviewed said, we need to take these people to court. And we found out it wasn't the History Channel that was responsible for the production. It was another company, and the company immediately went bankrupt after they gave the thing to the History Channel. So the History Channel said, well, try suing them. You're not going to get very far. They're no longer even in business. So that kind of stuff actually happens, which is why we train people, our scientists at Reasons to Believe, how to respond to an interview. And always be extremely cautious when they interview you for an hour, but you know they're only going to keep 15 seconds. They're just waiting for something that they can clip.
Thank you, Hugh. We're out of time. Would you please close us in
Be
prayer?
happy to do that. Father in heaven, we thank you for the amazing time in which we live. Thank you for giving us the privilege of being alive in the 21st century. That time that's spoken about in the book of Daniel, where knowledge is explosively increasing. Help us to use this explosion in knowledge and understanding to share with people the increasing, exponentially increasing evidence that you exist, you are the God of the Bible, and you have a plan to reward and bless every human being who desires to be rewarded and blessed and forgiven by you. In Jesus' name, amen. Thank you.